third RSGIS webinar appointment. So today we are going to talk about InSAR and what is about this technique and how and why this technique is interesting. I call it magic. We will have we will get some flavors about this this particular remote sensing based technique. This is the outline for today's talk, and I will go through a short introduction where we will have a look on how satellite radar sensor work, what is the principle, how do they work, and then we will go through conventional InSAR, and then we pass by time series analysis, InSAR, so advanced InSAR, and then we will go on some applications based on InSAR, such as earthquake, landslides, or man-made infrastructure monitoring, and then we try to draw some conclusion about InSAR and future developments and trends. So, what is a satellite SAR and how it works? SAR stands for synthetic aperture radar. With the limitation of time and scope of this talk, we cannot enter too much in the detail on how this system works. But anyway, we can say that radar or SAR sensors illuminate the Earth with a beam of coherent microwave radiation. Usually, SAR sensors works with three main frequency called X band, C band, and L band. And C band frequency corresponds to a wavelength of about 3 centimeters, while C band SAR corresponds to a wavelength of 6 centimeters, and L band to a wavelength of around 24 centimeters. So radar works in an active mode. So they generate pulses, and they also receive the backscatter pulses. This is the main functioning of this sensor. And why radar sensors, SAR sensors, are so important? Here we can see one of the main characteristics. On the left, we have a SAR image, while on the right, we have an optical image. These images are taken the same day in the same location. So radar sensors are all weather sensors. So they are, let's say, as a first approximation, independent from weather conditions. So the wavelength can pass through the clouds. So this is one of the main characteristics. So radar images can be acquired during day and night mode. So active systems no need external illumination. So there is no need of the sun's energy. So they are so-called all-weather systems. So the wavelengths can penetrate clouds, rain, partially dry sands, and partially vegetation. These are the main characteristics of SAR sensors, and they are coherent sensor, which is the main characteristics whenever then we go to see the phase of these signals. So radar sensors work along so-called azimuth, that is the direction of flight, and they transmit signal in a side-looking geometry. Usually these systems are right-oriented systems. So they transmit and receive pulses on their right side. So every line of the image is collected by a single pulse that is received during the acquisition. So image is built pulse by pulse. And the coordinate of the images are so-called azimuth and range coordinates. So whenever we talk about a pixel coordinate in an optical image is a row and column. When we talk about a SAR image, we talk about azimuth and range. So what is the product of a SAR satellite? The product of a SAR satellite is basically two products, are the amplitude and the phase of the backscatter signal. So the amplitude of a SAR image, it's very similar to an optical image. And the amplitude image is dependent on the amount of electromagnetic energy backscattered towards the radar sensor after the pulse is emitted, while the phase information is related to the sensor to target distance. This is very important in InSAR. So phase of recorded signal and distance between the sensor and the target that is illuminated is the main actor of this system. So I recall what the phase of a signal is. The phase is the offset of a wave from a given point. We will see a few slides coming. So as you can see, if the image, amplitude image is quite clear and can be interpreted with the interpretation keys we use with optical images, the phase image is unreadable. And the phase is known module 2π. And the phase image alone is of very, if not non-practical usage. So we cannot use a single phase image in a SAR system. So what is the magic of SAR interferometry? The magic of SAR interferometry is to try to compare, to try to compare two or more SAR images and try to see and try to highlight possible phase variations. Okay, so this is the main goal of InSAR. So phase comparison between two images taken in two different dates. So let's have a look a little bit more on details with a few sketches. So we have to imagine that the SAR satellite passes on acquire a scene from a defined point of view or orbit, okay? And then we have a certain event happening, and then we have a second pass of the SAR satellite. And the scene is acquired from a slightly different position, let's say almost the same position. This is a very key requirement in this technique. What we do is we use the unit of length, which is the wavelength. So instead, our ruler is made by our wavelength. And we measure in two different acquisition fraction of changes of this wavelength when this wavelength comes back to the signal. And these changes are strictly related to a difference of range between acquisition 1 and acquisition 2. So between acquisition 1 and acquisition 2, there might be some event that move the target with respect to the acquisition point. And this movement of target can be catched by measuring the phase of the backscatter signal. This is how this system works. So assuming that we have this movement of this target and we receive the backscatter signal, this backscatter signal will be recorded with a difference of phase with respect to the first acquisition. So by measuring phase variation on the left, this is what we do with SAR images, we can infer the range variation. As we said before, any range variation will imply a phase variation. What we do is by looking at the phase variation, we infer what was the variation in range that generates that specific phase variation. So this phase variation range as the wavelength modulo 2p or 2π, sorry. So this variation could be small entity or relatively higher entity. So we can monitor how this phase varies, okay, in a certain interval. And this certain interval has an amplitude of 2 pi, and usually it is measured by from minus pi to 2 pi, so that the interval is 2 pi. And this phase variation is, as I said before, this phase variation equals an equivalent range variation. Depends on the wavelength we use, depends on our system, which system we are using. For instance, if we are using a SAR C-band, SAR C-band has a wavelength of 56 millimeters. So to have a full cycle phase difference, we need to have range variation on only half wavelength, because the wavelength has to travel and come back to the sensor. So we need a range variation on only half a wavelength to have a difference of phase of a full wavelength. So this color coding appears clearly here. So what is a differential interferogram? A differential interferogram is exactly the product of an InSAR process, where we take, we have a first acquisition of a first SAR image. So we have the first phase image. Then we have a certain event that can happen if we want to monitor surface displacement. And then we acquire the second image. So we take the first image and the second phase image. Then we make the difference with more or less complex processing that is simplified here, and the final result is the interferogram. So what is an interferogram? The interferogram is a set of pixels that represent the phase variation. So every color here, as I explained in the previous slide, represent a phase variation in space. And every of these fringes can be then associated to a range change. And the range change represent what? Represent the difference of range between the satellite and the target on the ground. So if the target on the ground and the satellite change their distance, their relative distance, it means that if the satellite is considered acquiring the scene in the same exactly position or very similar position, it means that the target is moving with respect to the satellite. So by measuring the phase, we can infer the displacement. So here we can color code phase variation that we measure, of course, in radians from minus pi to plus pi. And we can then convert this phase variation into range variation from, in this range variation, magnitude is up to 28 millimeter per cycle in the case of SAR band C system. So making an interferogram now is relatively simple. Now we have softwares available that with few steps and with almost regular computers allow us to process modern SAR images, and it is relatively simple to process it. So the technology evolved. However, the interpretation of the image is not so direct and is not so straightforward. As we can see here, we have another interferogram of a cosseismic, it's a cosseismic interferogram for an earthquake in central Italy that happened in 2009. And every fringe here represented the formation of this portion of the Earth's surface. We can observe fringes where we have a so-called coherence, so where we have certain characteristics that keeps the variation of phase in time almost, let's say, similar. So we have certain geometric and physical characteristics that are similar between the two images. But we have other areas where we have this similarity not respected. So we will have so-called decorrelation. So in decorrelated areas, we cannot reconstruct the phase changes like we can do in correlated areas. So this is one of the problems of interferograms, and this problem of decorrelation cannot be addressed. So this is a loss of information. Then we have other problems in the interferograms that are depending on atmospheric influence. So what I said at the beginning of the presentation, that these are all-weather systems, yes, is still true. However, atmospheric problems in the troposphere and the ionosphere might change the velocities of the waves, and hence they can change the phase. So they might influence the SAR image when we look at the phase. So if the atmospheric conditions do not influence the amplitude, they certainly influence the phase. For this reason, regular interferograms are useful, yes, but we can overcome these two problems with atmospheric effects and decorrelation, not by using only 2 images at a time, but using time series of images. So conventional interferometry use a pairwise approach. So we build usually interferograms and we map displacement only by taking an image before the event and an image after the event. But with the time series approach, we use several images, several SAR images, 20, 30, 100. This technique is called persistent scatterer interferometry, or PSI. So with PSI, we overcome limiting factors of conventional interferometry, pairwise conventional interferometry. So we mitigate the problem of reflectivity changes that imply loss of the correlation, and we also try to mitigate atmospheric disturbances, as I said before, on troposphere and ionosphere. So how permanent scatter interferometry works? Permanent scatter interferometry works by looking at so-called persistent scatterers. So those scatterers, those elements on Earth's surface that they keep, let's say, constant in time, their reflectivity characteristics, both in terms of amplitude and in terms of phase. So there have been, in the recent years, some techniques that are aiming at selecting in the images this type of scatterers. So these type of scatterers are coherent, and the aim is to select these scatterers and make interferometric processes only on these scatterers. So what is a permanent scatterer? A permanent scatterer is a scatterer that keeps the phase, let's say, with constant, that keep this phase constant in time. So as we can see, here we have time in the x-axis, and we have the phase variation from -pi to +pi in y-axis. As we can see, in time, a non-permanent scatterer shows a high variation of the phase, while a persistent scatterer or permanent scatterer keeps the phase varying very little. So it keeps its phase almost constant in time. So the goal of persistent scatter interferometry is to select those pixels and then make interferometric processes only on these selected pixels. So these techniques evolved in time. So if before PSI technique worked well on persistent scatter interferometry, then it evolved, and now we are able to select so-called distributed scatterers. So those pixels that are, let's say, are not ideal PS scatter. They have quite good variability both in terms of density, both in terms of phase and amplitude, but they can still be used in the system, and the use of these distributed scatterers improved significantly the PSI technique. So let's say this is almost the third level in terms of development of InSAR technique. So, but what do we measure in SAR? What is the final measure that we can do with the InSAR techniques, both conventional or advanced technique? Assuming we have a displacement, the displacement can be represented with a 3D vector in the real world. So this 3D vector is observed along the line of sight sensor target, and can be observed in the line of sight. It means that we observe only the projection of this 3D vector along the line of sight. So with the satellite, it's very important to understand that any measure we do, both with conventional and advanced, it is a measurement of a deformation, or if you want, a displacement in this direction, okay? And usually we represent this displacement, as we said before, by color coding. And usually we represent a movement towards red colors as a movement away from the satellite, while a variation towards the blue colors, and we interpret those variations as a movement or a displacement towards the satellite. Okay, so if we have an increase of phase change, it means we are going towards the red. If we have a decrease of phase change, we are going towards the blue. If we have an increase of phase change, we are going to observe an increase of range. So the target goes away the satellite. And if we have a decrease of phase change, we have a decrease of range. So the target is moving towards the satellite line of sight. However, nowadays, not nowadays, this system has the capacity to observe the Earth surface with two different geometries. So in an ascending mode and in descending mode. And by combining images acquired with these two geometries, we are able to do what? We are able to combine these two vectors, and we are able to highlight two possible directions: the east-west component of the 3D displacement and the vertical component. Due to the acquisition geometry, and since these images, the SAR systems are on quasi-polar orbits, InSAR systems are not sensitive to the north-south direction. So at the end of the day, we measure displacement or line of sight, or if we combine descending and ascending geometries, we can isolate east-west components and vertical components. These are the type of measures that we do. Let's have a look on, in detail, what are the main approaches in PSI. So there are four main approaches. The first one is called PS InSAR. It's a register technique, and it was a breakthrough in InSAR and in remote sensing, but it was a breakthrough in geology itself as a all InSAR approach. It was the first complete solution looking at permanent scatterer approach, and it uses the amplitude coherence in time, stability in time, as a criteria to select PS and then do all processing. So it was a first solution to estimate the formation, to estimate the residual terrain error, and to separate this error from the atmospheric contribution. It works very well in urban areas with very high spatial density of PS, and with very high precision in terms of deformation estimation, displacement estimation. However, the main limitation of these techniques was that require very high coherent target. So these techniques fail in rural areas where we have very limited number of PS, or persistent scatterers. Almost in parallel, there was another technique developed at the beginning of the year 2000, and this was called small baseline subset technique, or SBAS technique. This technique selected PS not based on the amplitude, but based on the coherence. So it was able to select pixels, permanent scatterers, based on the stability of its coherence value in time. And then the main disadvantage, the main advantage was it was able to select good permanent scatterers also in rural areas. However, the density was a little bit lower than the PS InSAR technique, but the precision quite similar. The density was lower because it was working with so-called multi-looked images. If you work multi-look, it means degrading the spatial resolution of the images. So it, naturally, by degrading the spatial resolution of the images, you degrade the density in space of potential PS. So there are other two very important big steps in PSI. SBAS technique is still used and very efficient technique. There are two evolutions about, there are two evolutions of PS technique. One is called generically persistent scatter interferometry, developed by Hooper in 2004. And this technique differentiates from the rest because it selects PS based on both amplitude and it also has a phase stability criterion. And another big advantage of this approach is that we do not need a deformation model to estimate displacement like we need in the previous two models. And another very good advantage of this approach is that this has been implemented in an available open source software, so-called stamps. Previous technique PS InSAR, it's a proprietary software, so any a proprietary technique, so any software is available, while SBAS now is implemented in different open source softwares, including stamps also. Another very important development is called SqueezeR technique, which is an evolution of the PS InSAR technique. And the SqueezeR technique solves one of the problems of the PS InSAR. So it works well on rural areas. So now it is possible with this technique to have a good density of PS and DS in both in rural and urban areas, and these improve both in selection of the density, selection of the pixels, increased density of PS, and also increased precision and also accuracy of the measurement. So SqueezeR now is a reference technique on permanent scatterer interferometry, and again it is a patented technique. So what is the precision? When we talk about PS, what is the precision, expected precision? As other common GNSS techniques, or if you want any geodetic technique, each InSAR measures are differential measurements. So we need a reference point to make our own measures. So we measure the variation of a single target with respect to our reference point. So there is the need, okay, to select a good, stable reference point to which other measures are compared with. The precision depends on the number of images we are using. I forgot to say that any of the above-mentioned approaches are successfully applied if we use 20, 30 or more images. The more we have technically, potentially, and the better is our result. The better means high number of permanent scatterers and good estimation of the errors, and hence good estimation of the displacement. So to have a good precision and good accuracy, we need a good number of images, high number of images. We need high density of points, so we need to have a good physical condition on the ground, and we need to have a good algorithm that can estimate possible factor of influence like atmospheric factors, okay, and of course depends on the distance from the reference point. So usually good measures or the measures are more precise if we are measuring displacement of targets not too far from our reference point selected to do our measures. So, but in practice, we are talking about a precision of about 1 millimeter per year whenever we look about displacement rates or velocities, okay? And we are talking about line of sight precision of 3 millimeters whenever we talk about single measure. So these are the two big products, the two main products when we measure displacement with InSAR. We measure displacements and we measure displacement rates. So displacement in time. So let's have a look now on few applications. So now we will have a look on applications with a conventional InSAR approach and application with permanent scatterers approach. So let's have a look on how to have a look or how to have a picture of an earthquake with InSAR. And we take as an example a Lombok earthquake that happened in 2018 in Indonesia. It was a destructive, of course, a terrible earthquake with a huge impact on the population. More than 100 people were, over than 100 people were killed and left more than 20,000 people homeless. So this is an interferogram that has been built by using two SAR images, one taken before the event, before the earthquake, and a second one taken after the event. We said before that every of these fringe represent a displacement, and this displacement is represented by cycle. So how to interpret, in few minutes, how to learn how to interpret a SAR image. We said the basic point is to take a point of reference. So we should select one area in our interferogram that is considered as stable, okay? So this is our zero. It doesn't mean this is absolutely stable, but this is our zero. So when we make the measure, we will consider this as a stable. And then we start counting the fringes. So we count the first fringe, the second fringe, the third fringe, or if you want, the first cycle, the second cycle, the third cycle, and so on. The fourth cycle, the fifth cycle, and so on. And when we talk about the cycle, we talk about variation, in this case, from blue to red, to green, to cyan, to blue. And then again, from blue to red, to green, to cyan, to blue. So we are going towards positive changes of phase. But in another side of the interferogram, we see that this color coding is completely inverted. So if before we go from minus pi to plus pi, then we go from plus pi to minus pi. So we invert the order. So we can still count another cycle. First, the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth cycle, but with different sequence of colors. This means what? As we said before, we have to interpret this sequence of colors as movement away the satellite or towards the satellite. In the first case, in the southern part of this interferogram, we are going away the satellite, while in the northern part of the interferogram, we are going towards the satellite. So we can say that this central region is subsiding while the northern part region is uplifting. How much? To do this calculation, how much in terms of millimeter, we just apply what we saw before, and we convert the cycle changes into displacement changes. Every full cycle corresponds to 28 millimeters of displacement line of sight. So now the game is quite easy because we just can count the number of cycles and add to every change of cycle 28 millimeters. So by doing so, we can count how many millimeters the central part of the island displays with compared to what? With compared to our reference. In which direction? In this case, away from the satellite. In the north part, towards the satellite. So this it's very important principle. As we can see, the variation of phase is cycle. This is called wrapped interferogram. Wrapped because the phase is wrapped, okay, and it is variating cyclically between minus pi and plus pi. So if we make an ideal section from point A to point B, we can count the variation of cycles and we can plot in space this variation of cycles. So we have the 0, then we reach 2 pi, and then we start from 0 again up to 2 pi. So what we do by counting the number of fringes and by adding to every full cycle 28 centimeters is just doing this exercise. So we are unwrapping the interferogram. So if we have here relative cyclic measurement, here we have relative absolute measurement of displacement with respect to our 0 as a reference. So on the left side, in the bottom part, we have the wrapped interferogram, and on the right part, we have the unwrapped interferogram. And in practice, the unwrapped interferogram is our displacement map, which is our final product in our conventional InSAR application in this case. So we can say now that the earthquake had displaced this area in a, of course, with its own fault geometry, and the central part of this island went away from the satellite, so subsided, and the northern part of the island went towards the satellite and uplifted. Okay, how much? We have a color code around 20 millimeters in the 24 centimeters in the central part, and in the northern part 23 centimeters towards the satellite. So this was conventional InSAR application. Let's have a look now, really the magic of InSAR and how we can do more by exploiting not 2 dates, but tens of hundreds of images. So we will have a few applications, one to slope instability and another one to infrastructure monitoring. One is this one. So this is an area in Italy that is affected by slope instability, or if you want, easily speaking, landslides. So all these points we observe in the image are so-called permanent scatterers. So the big difference now with compared to before is that we don't have pixels anymore, but we have single points or single center scatterers. And these pixels, so this, what we are observing is so-called velocity field. So with permanent scatterers, we can obtain this kind of product where the green PS are so-called stable PS, while the colored PS are moving targets. So red, as we said before, is going away the satellite, while blue is going towards the satellite. In this case, we don't have any blue, so all these red points are moving away the satellite. And in particular, these are points that are going downward, and these are points of instability, of slope instability. These points are color-coded, so we can see more or less the rate of this instability. It's around some tens of millimeters per year, which is quite high velocity. But with InSAR, we do not have only displacement field, but for every permanent scatterers, we have how the displacement develop in time. So this is the time series of this PS. Every of these points is measured in terms of its displacement from the zero, from the reference point. Again, we need to select the reference and we need to measure the displacement of every permanent scatterer with compare to the reference. And this is the displacement measure. So we can measure the displacement of these permanent scatterers for every single date of our time series. And then we can, for instance, in this case, we can assume displacement model like this one linear, and the slope of this linearly modeled displacement is exactly the velocity. So what we are observing here in the displacement field is the velocity at which this permanent scatterer is displacing. Okay, as you can see, this permanent scatterer is quite fast. It's going very, very fast, up to 20 millimeters per year. This is another application to a man-made feature. Here, it's a work published recently in a high-impact journal on a disaster that happened a few years back in Italy on a very important transportation infrastructure. Here we are in North Italy, and this bridge was an highway connecting the north part of Italy with France, more or less. This bridge collapsed during a storm, during summer storm, and let's see how we can use InSAR to monitor such kind of infrastructure. So by applying similar techniques as we saw before, we can select few permanent scatterers, and for these permanent scatterers, we can observe how the displacement varies in time. And we can observe different permanent scatterers in different parts of the bridge. For instance, these two reds, this one, in the southern part, and this is the second one in the northern part. And as you can see, these two permanent scatterers that are likely separated by less than 20 meters, because these are calculated, are estimated with the high resolution SAR satellite, are having different displacement behavior. And the third one, which is here, has another displacement behavior. So these data can be used to infer what has happened before the collapse of the bridge. So all engineers, they can use this kind of information to understand what was the mechanism, what was happening just before, few days before the main collapse event. So we are talking about measuring millimeters from a distance of about 700 to 800 kilometers. Again, this is really the magic of this technique. From one phase image, we don't see anything. We combine two phase image, and we could observe something that could not, that was not able to be observed before. And if we use even more than two images, 20, 30, 100, we can estimate displacements with a range of 1, 2 to 3 millimeters, depends on which SAR satellite we are observing. So the same precision and accuracy that we can obtain in certain conditions in the field, we can obtain with a very high complex processing from a satellite observation. But what are the limitations of these techniques? Of course, as all satellite-based observation, we need to have a validation in the field, and still several limitations exist. First of all, we need for PSI approach a good availability of images. That is not always the case in many parts of the world. Luckily, now we have programs like Copernicus with Sentinel-1, and we have a good availability of images now, but only recently in the last 3 or 4 years or so. Another limitation is that still in rural areas, it's not very easy to have a good density of PS. I remind that good density of PS is a prerequisite to have precise and accurate measurements. So in rural areas, we still have and encounter difficulties. We made improvement, but we still have to develop algorithms that are able to select good pixels and good targets in such areas. And especially in tropical areas, we need to deal with atmospheric issues. So algorithms should go towards this direction to have a better estimates on the influence of the phase changes due to the atmospheric effects. Another important limitation from application point of view, or if you want from market point of view, if you want to apply PS technique as a marketable technique, is that we don't know the location of PS before processing the image. And even processing image could displace the location of the PS slightly because of several, let's say, components of this processing. So this is one of the important limitations where we want to bring this PS into a real object on the field. Because remember, PS, it's a kind of, yes, physical, but a kind of virtual scatterers within the resolution cell of SAR satellite. And then the cost. The cost is not a detail because, yes, there are SAR images that are available free of charge, like Sentinel-1, but other high-resolution SAR satellites in C-band and also L-band are costly. So if we want to apply PS-type technique, so we need to buy large number of images. So a cost still represents a limitation. And I also have to mention that processing InSAR, doing full InSAR processing chain requires high processing technology. So we need to have good computers, good processors. So what is the state, what is the availability of images and sensors today? Today we have at our disposal images from Sentinel, both 1 and 2 are available free of charge. Then we have Cosmos Skymed in C-band as well as TerraSAR in C-band. These are not free of charge, so you need to pay. We have a Radasat image still in C-band. And in L-band, we have Japanese satellite LOS-2. So these are the sensors that are available today in the market. And there are upcoming sensors soon that will increase the availability of images. Then this will allow the users to extend in time and increase the resolution of our InSAR analysis. Here we can see rapidly a comparison between conventional InSAR and PS approach, and we can see if we can observe displacement of about centimetric level. With conventional InSAR, we can go up to millimeter level with PS InSAR. In both systems, we observe line of sight displacement. So if we want to have east-west or vertical components, we need to combine the two acquisition geometry. And PS usually are released as a time series of displacement for each point selected, while conventional InSAR usually are classical pixel or raster-based product. And usually conventional InSAR is useful in coherent areas, while PS working on coherent target has limited this problem. So conclusion, we can spend few words. In this presentation, we have a very brief and quick view of InSAR. It's a very complex techniques, and to understand the detail of the data, to understand the result we obtain with our processing, this will require time and good expertise. However, we understood that this is very powerful, not in potential, but in practice. These patented techniques are implemented, and there are a few companies that are giving this InSAR analysis product as a service. So there are huge globally wide companies that they are monitoring constantly every single corner of the world, and they give as a service the series of displacing points. So this is extremely powerful technique. We saw that several algorithms, I showed just the 4 main, but there is a plenty of literature, especially in the last 5 to 10 years, where different researchers and different research groups have developed and improved PSI techniques in different directions, or with less density, or with higher density to specific application, geodetic application, hazard application, or infrastructure monitoring. So there are several techniques available now in the market. As we see, it was and it is still represent a good opportunity in terms of marketability of this technique, because, as I said, there are services available in the market. There are many governments, including Italy, for instance, or many governments in Europe that are using the service given by a specific company in terms of monitoring. And however, InSAR is not yet an easy-handling technique. It's a very complex processing. It's not like downloading images, push the button, and get the result. We need high-skilled technician to run a full processing chain. And we still need higher resolution satellites to improve the density of points, to have very precise, precisely located points. And as I said, we need very high performance computer to process big scene and large volumes of data. So here are some references that I use to make this presentation, and I would like to thank you all the viewers, and let's open the floor now to a Q&A session.
Thank you very much, Dr. Salvatore.